Superposition is another circuit analysis technique that applies to linear circuit. Before I jump into the details of what superposition is and how to use it, I want to say a few words about linearity. So superposition applies to linear circuits, and up to this point we have been dealing only with linear circuits. So what does linearity mean? Linearity means that you have additivity and homogeneity or scaling. Let me just explain it with an example. We have seen that the voltage across a resistor, for example, and the current, the relationship between them is given by Ohm's law. And Ohm's law is simply V equals I times R. If this is V, for example, and this is I. So the relationship between I and V is linear, and when we drew it, it was just simply a line. That's what it was. And we also applied KCL and KVL. For example, KCL at a node was like I1 equals I2 plus I3, something like that. Without getting to the details, the idea behind it is like everything you see in here is linear. I don't see anything that is I squared or e to the power I. I don't see any of those. Similarly with KVL, we did I did show you, like, if you have a bunch of elements around the loop, what you did is you said, well, V1 plus V2 minus V3 equals 0. So this is also linear. There's no V squared, there's no e to the power V. All of this is linear. So as it turns out that if circuits follow this linearity rule, we can use what we call superposition. So let me explain what superposition is. So superposition in simple terms applies to the following. If you have a circuit like this that contains multiple sources, what superposition tells you is the voltage across or the current through any point within the network is simply the algebraic sum of these individual contributions from each one of these sources. So what does this mean? Well, let me just give you that with an example. So let's assume that what we want to do is to compute this voltage here, this plus minus, and I told you let's compute what this V is. I haven't given you the value of IS or the value of VS, so we're going to keep it in these terms, and that's on purpose. All right, so, well, there are multiple circuit analysis techniques that will give us this. For example, you can use mesh or you can use nodal analysis. So I'll use nodal. I'll put my reference in here, for example, and that will be simply, that's the V that I'm looking for. So I'll write these nodal equations, for example, this current, then this, and then that, okay? So we'll say V here, we'll say V minus VS divided by 6 plus V divided by 6 minus I of S equals 0. And of course, if you do a little bit of algebra, you'll end up with the following equation. V equals half of Vs plus 3Is. So this is what I want to focus on at this point now. So what this equation tells me that the voltage across this particular resistor in the circuit is simply the result of the contribution of the voltage source and the current source. That's what you see in here. So the it's like, well, half of the voltage source and 3 of the IS. That's what this tells me. And if you think about it, this equation here is linear. But okay, so the voltage here is the result of VS and IS. Okay, so how does that help us in terms of superposition? Well, as it turns out to be that if I take a look at the effect of each one of these sources individually and I add them up, we should get that V. So let me show you. All right, so what I will do is I'll turn one source at a time. So first I will turn off this particular source in here, which is the current source. So how do I turn off a current source? So this is one of the procedures for superposition. So you have to turn off sources. So at this point I want to turn off this source, and simply if I want to turn off this source, I want the current that is flowing in here, IS, to be 0. And the way we typically do it is by basically opening the circuit in here. So if there's no wire, you basically turned off that source. So let me just draw how this would look like. So the circuit would look something like this. This is plus, minus, and then I have the 6 ohms in here, and I have this one here. Okay, that still is VS, that's still 6 ohm, and this is also another 6 ohm, and this here still, at this point, it exists, and here. So what happens is I open the circuit in here so that the current doesn't exist. And in this particular moment, IS for this particular sub-circuit is actually just 0. And of course, you might be thinking, well, if the current in here is 0, that means this doesn't exist because the current is not part of the circuit, and you're absolutely true. So what we're looking for the following. We're looking for this particular voltage, but now I'm going to call it V prime because it is not the same exact voltage in here, at least not yet. Okay, so how do we do that? Well, simply if you take a look at the circuit, if you're interested in V, Okay, you're interested in this particular, or V prime. This is 6 ohm, this is 6 ohm, that's a Vs, so it's just simply voltage divider will give me that. So I can just simply say V prime is just Vs times 1/2, okay, because half because it's like the two resistors are the same value. All right, so now what I will do is I turned off this source. Now I'll turn it back on, and then I'll turn off this source. And of course, if you turn off a source that is a voltage source, the way you do it is, well, the voltage across 2 points on a wire is 0, because what I'm aiming for is V to be 0. So basically, you just replace it with a short circuit or just a wire. So let me just draw this. So the second circuit will be, instead of Vs, I'll just basically replace it with a wire. I have the 6 ohms in here. I have the 6 ohms in here, okay? And then I have the 12 ohms in here, and then the current source now is Is, okay? So what are we looking for? Well, it's pretty much the same voltage. I'm looking for the voltage across this particular resistor in here. I'm going to call it V prime prime because it's not the same as V prime and it's not the same as V. All right, so if I'm interested in this particular V, there are multiple ways we can get to it. We can either say, well, you can apply current division and so forth. Well, actually, we can't apply current division, at least not yet. What we can do is either use nodal analysis, or I can combine these 6 and this 6, and then I basically figure it out using the I. So what I'll do is I'll combine these two 6s in here because they're in parallel. So that will give me this particular circuit now, which is just simply some resistor in here, 12 ohms. And then here is the Is, okay? What's the value of these? There are like 6 and 6 in parallel, so that should be 3 ohms in here. So the voltage I'm looking for is still the same voltage in here, that's V prime prime. So that will tell me that the V prime prime is just simply 3 times Is. That's what we have, basically, because I know the current going through it, so all I have to do is just multiply it with 3. All right, so let me just highlight this here. Okay, so we'll move this here, and I'll highlight this as well. So what I want you to see is the following. So what does superposition tell me? Well, superposition tells me, and I can see it in the equation at this moment here, that if you want V, what you have to do is just say V prime plus V prime prime, and you will get half Vs plus 3 Is, which is the same as this particular equation we started with. So what superposition tells me is that this V, or any V, any voltage in the circuit, or any current throughout a linear circuit, when everything is linear like what we have in here. So if you're interested in that particular voltage, well, simply it's the effect of Is and Vs and combined or added. This is because it's linear. So what you do is you can turn off the source, each source at a time, and then can figure out the contribution of that source, and then you can just basically sum the results, and that will be superposition. You superimpose the different voltages of it. So you might be wondering, why are we doing this? Couldn't I just basically use nodal analysis and get done with it? And you're absolutely true in thinking that way. It's like, hey, yes, the resulting circuits in both cases are simpler than the one in here. I didn't need to use nodal in here or here, but that's not always the case. In superposition, the resulting sub-circuits in here will be always a little bit simpler. Well, most of the time will be a little bit simpler, but still, it's a little bit more tedious. I'm solving 1 and 2 circuits in order for me to get that instead of just writing one equation. So what's the point of having superposition? Well, as it turns out that if these sources in here are of completely different nature, so at this point, everything we deal with is DC because the math is simpler. But later in circuits, you will encounter sources that are completely different in terms of fundamentally different. So this Is might be an AC with, like, let's just say 120 hertz, for example, and this one here, it might be an AC with like 40 hertz. And if that's the case, to combine them with like that, with the V's, it becomes a lot more complicated because we're going to have differential equations and so forth. Or maybe not differential equations, but like we might have to transfer to a different domain. Anyway, the math will be a little bit more complicated if I just deal with the circuit this way. Well, I have like 2 sources of completely different nature. They're not DC, and that they don't have the same frequencies and so forth. So as it turns out that if you do superposition, for example, you'll be dealing with an AC source that is 40 hertz. That's it. So everything in the circuit is just 40 hertz, and this one here will be 100 hertz, for example. So the circuits that results will become a lot easier to compute and a lot easier to deal with, and that's where superposition comes in handy. All right, and one more note before I actually jump into examples and exercises. So voltage, the superposition applies to any current. Like for example, if you're here and you wanted to compute this current, you will be able to do that. If you want to compare this current, you will be able to use superposition. However, this applies to voltages and currents, but it does not apply to power. Not power. Because power, if you think about it, is P is simply I times V. The relationship between I and V is not linear anymore. Okay, and you can think about it as well in terms of like, think about the resistors. So resistors, I think it was I square R or V squared divided by R. I forgot. It's like whether, I think it's I square R. Yes. V equals IR. Yes, it's I square R and V square R. So if you think about it, this is I squared and this is V squared. So you can't say, well, I'm going to compute the power in here and then the power in here and just sum them. That does not work in terms of superposition because power is not a linear variable.